Okay, so with this podcast, we're going to continue adding to our lovely list of probability rules. Let me guide you to this lovely box in your book right here. Let's start with some definitions. Two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E affects the probability of event F. So in easy language, if I go to the dentist and I get a cavity, that has no bearing or no effect on the probability that you go to the dentist and have a cavity, right? Or if I go out to my car and it's so cold that my battery's dead. The probability that my battery's dead has no bearing on the probability that your battery is dead. Okay? Other than the fact that we live in a cold area. But the notion is, when you're about to determine probability, you have to ask yourself, are the events independent or dependent? Here's another classic example. Okay? You have 3 green M&Ms and 2 red M&Ms in a bag, right? You reach in and you grab an M&M. And then you reach in and you grab a second M&M. What's the probability that the second M&M is red? And you say, well, that depends on what the first M&M was, if you're doing an experiment without replacement. If I were to replace that first M&M and put it back in the hat, then it has no bearing, it's not going to affect the probability of what the second M&M was. So basically in our near future, we're going to start to talk about with replacement and without replacement and how that affects what we do when we do our calculations. So let's take a look at the next box. And I wanted to remind you that, yes, it looks like I'm reading out of the book right now, but my goal is to do some cherry-picked problems from the text in about a moment. So, okay, multiplication rule for independent events. If E and F are independent events, then the probability, and I'm going to write this bigger here and more formally, the probability of E and F, I'm using the mathematical symbol, would be equal to the probability of E times the probability of F. Okay? So that's what this is saying right here. So you say, all right, if I know I have independent events, then I'm just going to multiply the two probabilities. Okay, and in this next lovely box here, I'm going to have to translate this one for you in easier language. The multiplication rule for n independent events. So I don't really like the notation there. What that basically means is if event E, F, and G are independent, then the probability of E intersect the probability of F intersect the probability of G. If we know that events E, F, and G are independent, we can just go ahead and extend. We're just going to extend that multiplication rule. So we'll just take the probability of E, times the probability of F times the probability of G. So all we're really saying with this rule here is that we can extend that to more than 2 events. What if you have 5 events that are independent? You can just multiply all 5 of those probabilities. So I really like to just think of this as an extension of the rule that we just talked about a moment ago. Okay? All right, let's take a look at the next one. Okay, and the final magical box, which I really like for today, is sort of a summary of all the rules that we've talked about thus far. So I'm going to put a big star on this box. It says the probability of an event must be between 0 and 1 inclusive. And it says, writes that more formally. And then for number 2, it says the sum of the probabilities of all the outcomes in the sample space must equal 1. Okay, and that means that if you are looking at all possible events, like we talked about before, like if you're rolling a fair die, what exists on the faces of a fair die? Even and odd numbers. So the probability that you roll an even plus the probability that you roll an odd, better equal to 1. So it does. 3 out of 6 plus 3 out of 6 equals 6 out of 6, which is 1. So here in number 3, if E and F are disjoint events, that means that they don't have any intersection, they're mutually exclusive, then the probability of E or F is equal to the probability of E plus the probability of F. And again, in the last podcast, we talked about, what if they're not disjoint events? Well, then you're going to have to subtract out the overlap. right? So we talked about that in the podcast before. I just really wanted to draw you to this summary here. I also wanted to talk about the idea that the last rule, number 5, is that multiplication rule for independent events. Now that one we didn't get to play with, so now it's time. I'm going to pick a couple problems from the book and let's do this. Okay, so I am going to be picking number 17 here, and I'm going to read it for you. It says the probability that a randomly selected 40-year-old male, it may look a little blurry to you because of the font. Let me see if I can actually, let me hit pause and try to zoom in. Okay, maybe that font's a little bit better for you. So the first question is, if the probability the 40-year-old male will live to be 41 years old is 0.99757 according to the NVSR report, what is the probability that 2 randomly selected 40-year-old males will live to be 41 years old? You think, wow, that's kind of a grim question, but it's someone's job who works for an insurance company to think about these kinds of things, right? That's why people going into actuarial science, they start off with a foundation in probability, right? So, okay, so basically looking at, let's see if it'll let me write on there, the probability that 2 males, I'm just going to write it like that, the probability that 2 randomly selected males will live to be 41 years old. Well, first you ask yourself, are these independent events? And you say, you're assuming yes. So the multiplication rule for independent events says, basically the probability that both of these males will live to be 41 years old, we're going to have to take the 0.99757. So we're basically going to have to take this number right here. And again, 0.99, kind of running out of room there. Let's see if it'll let me erase it. There we go, 0.99757. So basically, you're utilizing that multiplication rule for independent events. And you say, well, why am I multiplying? Well, think about it. There's no way you're adding, right? Because if you add 0.99 plus 0.99, you're going to get something over 100%, which wouldn't make sense. Also, go ahead and do it, and we'll talk about why the answer makes sense. So you're ending up with what? 0.995? And I'm rounding to the thousandth, but so you're ending up with about 0.995. So what does that mean? That makes more sense because the probability that 2 of the males survive, or that live to 41, of course should be less than the probability that 1 male alone. Intuitively, if I'm taking 2 of them, the chance that they both make it to 41 should be a little bit less than the chance that one of them alone makes it to 41. Okay. Let's try the next one. The next one says, in part B, it says, what's the probability that 5, and I kind of probably should have highlighted that instead, but basically that 5 randomly selected 40-year-old males live to be 41. Okay, so now I'm going to erase this, and all we're doing is we're saying, okay, instead of looking at 2 males, now we're saying 5 males. So the probability that 5 males live to be 41. Well, you say, hey, aren't those independent events? Yeah, we're assuming that. So you would think, 0.99757 times itself, 5 times. But you guys are pretty good at algebra, so hopefully, you're realizing that's 0.99757 raised to the 5th power. Good. So let's go ahead and crunch that out. So 0.99757. I'm operating on the calculator along with you here. And so I'm getting about 0.9879. And depending on where you're rounding, 0.98791. Okay? So basically the answer to part, let me see if I can zoom in there. This is B. So the answer to part B then would be 0.98791. Okay, now let's take a look at part C. Now this gets tricky. It says, what's the probability that at least one of the 5 randomly selected males will not live to be 41 years old? Okay, and so they're really getting kind of tricky in the language here. They're saying at least one will not live to be 41. So I really want to strongly encourage you with this kind of problem, and I'm even going to highlight this in another color. Whenever you see the words at least one, so the probability that at least one does not live to be 41, the trick is you use the complement rule. You do so because at least one means one or two or three or five of those five randomly selected males. So you use the complement rule, and you actually take 1 minus the probability that none do not live to be 41. So you're going to see us doing this a lot. So basically the opposite of at least one is none. So you're using the complement rule. So you're taking 1 minus the probability of none. But then you get, here you've got this double negative. The probability that none do not live to be 41 means the probability that all did live to be 41, and we had figured that out in the step above. So long story short, in part B, we had figured out that the answer was 0.9, let me see here. We had figured out that the answer was 0.987. Oops, I'm looking at the wrong number here. Yeah, so in part B, we figured out the answer was 0.9879. I have to grab my book here, put on my lap, 0.9879. And basically, rather than us directly calculating the probability that at least one does not live to be 41, we're going to utilize this complement rule, and we're going to take 1 minus the probability that none do not live to be 41. But none do not live to be 41 means all did live to be 41. So I know this is tricky with the language. Easiest thing I can say is you're going to take 1 minus the thing that you had figured out in part B. So after all said and done, for part C, you're going to take 1 minus 0.9879. Whatever that leads you to, that's going to be your answer. So 1 minus 0.9879. So 0.0, and I'm checking my answer key as I do this, and yes, so you will arrive at 0.012, rounded, 0.0121. Okay? But the biggest thing is that we have to start getting used to the fact that we're going to be using this complement rule a lot, and we're going to be triggered by the words at least one. Okay? Let's try another problem so that you can start to believe that. Oh, it does ask, would it be unusual if at least one of the 5 did not live to be 41? And what we would say to that is, yes, that is unusual because the probability we computed is less than 5%. Remember, to your author, unusual means less than 5%. Okay, let's try another one. Okay, so the next one that I have picked is number 26, about NASCAR. And I think I'll probably just write in the margin here. It says, among Americans who consider themselves racing fans, 59% identify NASCAR stock cars as their favorite type of racing. Suppose that 4, and again I always underline these key, suppose that 4 auto racing fans are randomly selected. So again, we're assuming these people are independent of one another. What is the probability that all 4 will identify NASCAR stocks as their favorite type of racing? So you might be thinking, hey, that's the multiplication rule for independent events. And you're right. So for part A, we would be taking, you might be thinking, all right, we're going to take 0.59 times 0.59 times 0.59, 0.59 times itself, 4 times. But that means the same thing as 0.59 to the 4th power. Okay? So let's go ahead and crunch that out. So this will be part A. So 0.59 up caret 4. So you're looking at about 0.12. Okay? So the answer to part A is 0.12. Now let's go ahead and take a look at part B. What is the probability that, see, at least one, I told you this was going to come back at us. What is the probability that at least one will not identify NASCAR as his or her favorite type? Well, I always translate because they really start, messing with the language in some of these problems. So let me erase this. At least one will not identify. I translate this. Okay, so the probability that at least one will not identify, I'm just going to shortcut the language there, will not identify, NASCAR as their favorite, according to the complement rule, would be equal to 1 minus the probability that none will not identify NASCAR as their favorite. But here's the kicker. None will not is a double negative. None will not means the same thing as all will. And we had figured out that all will in part A. So if you're saying to yourself, well, gee, then we're just going to take 1 minus the answer that we had gotten in part A, that's right. Now, it's not always the case. I know it just happened in the problem that we did before, but yeah, so basically, long story short, in part A, we got 0.12, and in part B, we're going to take 1 minus that 0.12, and we're going to get, 0.88. And I'm rounding here, of course, 0.88. But the idea is that we're constantly utilizing that complement rule. Okay, so the probability that at least one will not identify NASCAR as their favorite is equal to 1 minus the probability that none will not identify NASCAR as their favorite. But none will not means all will, and we had figured that out in the part above. So, all right, let's try it again. Part C. What is the probability that none will identify NASCAR as their favorite? Now, this is just blatantly asking us to compute that probability, so let me talk that through with you here. As I erase that. Okay, so the probability that none will identify NASCAR as their favorite, well, think about it like this. What's the probability that one person alone wouldn't? Well, 1 minus the 0.59, right? So in other words, the opposite of this 59% is 41%. So 41%, you could even write that here, 41% would not have NASCAR as their favorite. I'm just going to write here, don't like NASCAR as their favorite. So then, if I select 4, what's the chance that all 4 of them say they don't want NASCAR as their favorite? So maybe you're thinking that's the multiplication rule again, but using the 0.41, the 41%, and that would be correct. So for part C, we're going to take, 0.41 times 0.41 times 0.41 times 0.41, which you already know means 0.41 raised to the 4th power. So if you're thinking that you're going to arrive at 0.028, that is correct. So for part C, I can just write here, I'm going to write on top of it, C is 0.028. Okay. Then, in part D, what is the probability that at least one, again, they're going to get us with that at least one, but they're always twisting the language. I'm going to pick a different color here. What's the probability that at least one will identify NASCAR as their favorite type of racing? All right. So again, so that I don't get tricked, I always map out the language. Okay? I'm going to map it out. I think I'll go back to red here. The probability that at least one identifies NASCAR as their favorite. Identifies, I'm just going to write NAS. Well, I'll just write it, NASCAR as favorite, is equal to 1 minus the probability that none ID NASCAR as their favorite. Okay? But what's the probability that none of them ID NASCAR as their favorite? Oh, you had figured that out in the part above, in part C. So, it's coincidental that it's designed this way, but basically in part D, you end up taking 1 minus that which you found in part C. So, long story short, you end up taking 1 minus what you had computed back in part C, which was the 0.028. Okay? So 1 minus 0.028 is going to lead you to 0.972. So if you just want to record the answer, 0.972 would be the answer to part D. Okay? But the real thing is, I just want you to get comfortable with, if I can just really reiterate that, every time you see the word, and I'll highlight it right here, at least one. Okay, so the probability that at least one will do something. It's really 1 minus the probability that none will do something. So you're always utilizing that complement rule. All right, hope that helps. I think I only have, yep, I only have one more. Let me hit pause and get that. Okay, and last but not least, I'm going to pick number 28 here. I'll read it first. It says, suppose a satellite defense system is established in which 4 satellites acting independently, so they're blatantly saying independently here, have a 0.9 probability of detecting an incoming ballistic missile. We would hope it would be higher than that, but what is the probability that at least one, see again, what is the probability that at least one of the 4 satellites detects an incoming ballistic missile? Would you feel safe with such a system? So at least, the thing is, at least one of the 4 satellites means 1 or 2 or 3 or possibly all 4 of them. But for you to compute, those probabilities and union them all together would take a heck of a lot longer than just doing the complement rule. So basically, why don't we just take 1 minus the probability, the opposite of at least 1 is none. So 1 minus the probability that none of the 4 satellites detect it. Detect the missile. Okay, and so, well, how do you do that? Well, let's focus on first the probability that, none of the 4 satellites detect the missile. Well, if you got a 90% chance of detecting the missile, then you got a 10% chance of not detecting the missile. So if I zoom in on this fact, if I zoom in on trying to calculate the chance that none of the 4 satellites detect the missile, then I'm basically going to be taking, 0.10 times 0.10 times 0.10 times 0.10. That's going to be the chance that none of the 4 satellites detect the missile. So that's 0.10 to the 4th power, basically. So you get scientific notation, right? So that's 0.0001. Okay? But the thing is, this is the probability that none of the 4 satellites detect it. We want 1 minus that. Okay? So now minus 1, or 1 minus that. And so basically you're getting 0.9999. So the answer, the final answer to this one is 0.9999. And it says, would you feel safe with such a system? You say, well, hey, that's a pretty high, that's almost 100% chance that at least one of the 4 satellites is going to detect it. So that seems pretty secure. You can never get that perfect 100%, but that's pretty close. All right, guys, there will be a PDF of guided notes that are all encompassing all these rules that we've talked about. And good luck.